That's it.
Okay, so good. So today I want to discuss Banach-Colmez spaces. So first, a little reminder from last time, just to remind you what we did last week. For all the talk, I always fix E to be a local field with residue field, finite residue field FQ, and I choose a uniformizer pi. So basically, there are like two situations, right? Either E is a finite extension of QP, or we are in positive characteristic, and E is a field of the Laurent series over the finite field FQ. So that was the first piece of the data. And then the other one was we chosen S to be a perfectoid space over FQ. So my notation I use to denote the category of all perfectoid spaces over FQ. So basically, this is an p-adic space, which locally is of the form spar RR plus, where R is a Tate ring over FQ, which is perfect. This is really what this condition of being perfectoid means in characteristic P. And to the datum of E and S, we attach an p-adic space over spar E, which is a so-called relative Fargues-Scholze curve for E over S, and denoted by XSE, and it was defined as a quotient by some Frobenius operator of another p-adic space Y, defined using bit vectors. Okay, I did not have so much time to really discuss the geometry of the Fargues-Scholze curve, but maybe I can say that if you want to read more about the curve itself and its properties, like there are two good references at least. So there is a paper by Fargues and Fontaine in the proceedings of conference in Durham. You can find it on the web page of Fargues. And another nice reference is the Bourbaki report of Matthew Moore. So in both papers, you will find a much more detailed discussion of the geometry of the Fargues-Scholze curve, where when S is a geometric point, which is the case where the curve was first defined and studied. Okay, and on this, if we specialize the discussion to this situation where S is a geometric point, so spar C, C naught, C being a complete algebraically closed field over FQ, then we also saw that there is a nice classification of vector bundles on this curve. And more precisely, we saw that there is a natural functor from the category of isocrystals over E towards vector bundles on this curve. And the claim, which is a difficult theorem of Fargues-Fontaine, is that this functor is essentially surjective. So because we know what this category looks like, again, explicitly, completely, this just means that any vector bundle E on XSE, maybe I should write XCE to make clear that S is not a general perfectoid space, but really just a geometric point, is of the form, it's just a finite direct sum of vector bundles attached to this simple isocrystal of various rational cells on the I between 0 and 1 on R are rational numbers. So it looks a bit like the classification of vector bundles on the complex projective line, except that now you see rational numbers instead of just integers. And yeah, that's a difficult result. There is a new proof of this in the paper of Fargues-Scholze, which is in some sense simpler, but uses also more technology. Already the classification of line bundles is non-trivial. So the line bundle, the claim is that the Picard group is isomorphic to Z. For each integer D, you unique line bundle of degree D. And so
this functor is also faithful, isn't it?
Yes, but it's very far. Yeah, it's very also. I should repeat this again. It's this functor is very far from being full. There are many more morphisms in the category of vector bundles than there are in the category of isocrystals. So classification of line bundles is already interesting. And there is a nice discussion of it in the first chapter of Fargues-Scholze's big paper. Namely, it's connected to Lubin-Tate theory, Lubin-Tate formal group. So I don't want to enter really into this, but I can just say that something that can be proved is that if you have a perfect fluid space, let's say affinoid perfect fluid over HQ, and you have some untilt S sharp over E. There is an identification between the space of global sections, let's say, yeah, on the Fargues-Scholze curve for any over this affinoid perfect fluid S of this line bundle O of 1. So the construction I gave of this functor, I made it only when S is a geometric point, and only in this case when it's able to like prove such a statement. But the construction was making sense over any, if I replace this geometric point, but any perfect fluid space in characteristic P. So, for example, this vector bundle is always defined on XSE, whatever S is, and so this is an E vector space, right? And there is a natural identification between this E vector space and what you obtain by taking the evaluating on this untilt, on the first part of this untilt, the universal cover of so this is universal cover of the Lubin-Tate formal group law G over O, which is endowed with a structure of an E vector space precisely using this, like it has an OE module structure coming from this formal group law, and then because you take this inverse limit over multiplication by pi, you make multiplication by pi invertible, so it's naturally an E vector space. So there is, yeah, there is this interesting and a priori a bit curious relation between line bundles on the Fargues-Scholze curve and Lubin-Tate formal group laws, and Fargues-Scholze in their new proof of the classification result theorem, they use various properties of, say, for example, the logarithm map for this Lubin-Tate group law to check various claims about line bundles. And we will see this this fact reappear later, so that's why I wanted to mention it here. Okay.
Can one give the global sections of O, for example, 1/2?
Yes, so O of 1/2 is, if you look at the degree 2, so you have your local fit E, which I fixed, and then you have, for any H, you would have the degree H and ramified extension of E. And then this vector bundle here of slope 1/h is just a push forward of 1 on the Fargues content curve attached to h. So phi h would be the map from the Fargues content curve of this arbitrary extension of degree. It's not a line bundle anymore. So if lambda is d/h, d is the degree and h is the rank.
Ah, okay.
Yeah.
Okay, okay.
So that's why line bundles correspond to integers. No, no denominator. So yeah, then you can use this. Okay. So now I want to discuss what can be said about, various results about vector bundle on more general perfect weight basis. So what about? So we have this nice classification theorem when S is a geometric point. Of course, you should not expect to have such a classification for any S, but you can still pull some structural results about vector bundles. We start with a definition. So first, I recall what the vector bundle is, and even if this was already used here. A vector bundle. So let S be to spaces over Q. So a vector bundle over XSD is just a finite 3. I already said this last time, but let me just repeat it. And I also want to define another notion, which is the notion of a flat coherent sheaf. Over XSE. So this is an XSE module, which can locally, for the analytic topology on this relative Fargues content curve, be written as the co-kernel of the fiber-wise on S injective map between two vector bundles on XS. Okay, so definition is just that locally on locally on XS, I can, if I call this OXS module F, I can find a presentation of this form. Well, E and E prime are two vector bundles, and this map is injective and remains injective whenever if I base change along any geometric point of S. Okay, so why in algebraic geometry over a relative curve you could make a similar definition, and this would be equivalent to saying that you have a coherent sheaf on this relative curve, which is flat, not over the relative curve, of course, but over the base S. Here there is no map from XSE to S, so that will not. I cannot make an analogous definition, but instead I can use this other point. So I won't really use this notion today very seriously, but it will be useful next time. And some examples. Well, of course, any vector bundle is a flat coherent sheaf. But other class of examples. So I remind you that we have seen last time that untilts of S give rise to Cartier divisors on the relative far content curve. And so if S is an tilt of S over E, so corresponding to the embedding of S sharp inside this SE, and then forward of the structure shift S sharp along this map. This is also an example of a flat coherent shift. Stress cover shift setting.
If you have a Cartier divisor of degree 1, which is a flat coherent sheaf, does it necessarily correspond to an untilt then? Is that a precise statement?
If you have a flat coherent sheaf of
a Cartier divisor of degree 1, which is a flat coherent sheaf in this sense, is it necessarily arising from this construction? Like, is this the right way to say relative effect of Cartier divisor for S?
Yeah, I guess that would be probably correct. Yeah, I cannot. I'm not sure 100%, but I mean there is a well-defined notion of closed Cartier divisor in this case, which is discussed in the Berkeley maths. But that's probably equivalent to that. Yeah, I guess. Okay, so now comes another definition. So I want to define the V topology. So the V site on all perfect spaces of characteristic P. So the underlying category is the category of perfect spaces over FQ. And so I want to render this with a certain Grothendieck topology. And what you do is that you declare that a collection is a cover if it is and
it's not a finite collection.
It's not necessarily finite, no. But no, I put a condition that for each quasi-compact open, U in S, we want that there exists finite subset J in I, and for each I in this finite subset J, some quasi-compact open UI in SI, such that the images of this UI cover U. U is the union over IJ. Okay, so
Isn't the first condition?
yes, yes. You mean it's redundant?
Yeah.
Yes.
Do you really mean this, or do you mean F inverse U equals union I and J UI?
I think I mean this.
Why should F I of UI be? Oh, it is open. Oh my god. Never mind.
No, it's what? Sorry. That's the condition I put. I think it's all right. Yeah. But F I need not be open.
No. No. I think I'm confused.
Okay, what is a bit? So it's some kind of analog of the FPQC topology in this setting. except that, well, I think in the definition of the PQC cover, one puts an analogous condition. But it's true that usually there is this flat in PQC, you put some condition on the map. Here there is no condition. So it's a very fine topology, and it's a bit surprising that you can do anything with it, but this is what Scholze was able to do. Maybe I can make two remarks about this definition. Something which is not a cover is a counterexample. If you take, say, the point, then the origin in the disk, okay, some say non-Archimedean field. And you look at the disk over K, or maybe let's say the perfectoid version of the disk, because I only define this topology in the perfectoid setting, and you remove the origin. Okay, so this is not the cover of the perfectoid disk. Right, because if you look at say a disk of smaller radius around the origin, you won't be able to cover it in this way, right? Because yeah, I mean, if you take some quasi-compact open inside here, it will be contained in the annulus of radius r and 1 for some r between 0 and 1. So just to see how this condition what looks like in practice. And something else I should say also is that if F is a morphism between two analytical spaces, so analytic, I recall, means that it's locally the adic spectrum of a Tate pair instead of just a general Hooker pair. Then, if you look at the underlying map on topological spaces, this map is generalized. Meaning that if it contains a point, it contains also the image of F also contains generalizations of this point. Basically, it comes down to the fact that in the analytic world, generalizations of the point, like they form this totally ordered chain of points that correspond to the spectrum of evaluation. So in particular, if F is surjective, then the underlying topological map is a quotient map.
And so how was this related to?
This is because I think, for example, this topology looks also a bit like the H topology. And I think in the definition of the H topology, one has a similar issue a priori, and one puts a condition, which I forgot now, to ensure that to get around this issue. But I was pointing out that in the analytic setting, this issue does not appear because any subjective mark is automatically a quotient.
For me, it makes me more comfortable with what you wrote with the FI of U,
Yeah,
because it's generalizing is just like
Like,
basically the same as open, but without finding it.
For example, this will imply that if you take a topological space and look at this underline,
Yeah.
This implies that if how do I want to call it, Z is a topological space as a functor underline Z, which sends S in perfect Q, in a constant function of this topological space of S to Z is a V sheaf. Okay. And difficult result of Scholze is that the V side is subcanonical, meaning that any representable pre-sheaf is in fact the sheaf for the V topology. So in particular also like the sheaf O, which we just send S to global section of the structure sheaf on S and the sheaf O plus. There are these sheaves.
Am I right? The second one has higher cohomology, but the first one doesn't? Or
that's correct, yes. But I mean, it has almost no cohomology in positive degree. If you work in this almost categorization. But that's correct, yes. This may have higher cohomology and not the other one. Yeah. So basically, the argument first one uses this topological fact to reduce to the affinoid case, for like to the case where you have a V cover which is formed by some affinoid perfectoid space covered by something affinoid perfectoid using point 2, and then basically when it is reduced to proving that this is indeed a V sheaf. The pattern of the proof is something very typical of all the V descent statements that Scholze proves. First, you do a pro-étal cover, so something which is an inverse limit of étal morphisms, to get to an adic space which is now what Scholze calls strictly totally disconnected, which is basically just a profinite union of adic spectra of geometric points, like things of the form spa C++. And because C+ is a valuation ring in C, then he is able to prove that. So you argue everywhere modulo some given uniformizer, and he is able to prove some kind of automatic flatness statement over in this situation, because everything is just a valuation ring. So this means that basically proof of V descent is decomposed in 2 steps. One is pro-étal descent, which means, I mean, it's not easy, but it can be done by reducing to like étal descent. And the other step is some kind of automatic flatness, like flat FPQC descent, once you are over this weird, frightening, strictly totally disconnected space. But yeah. Many descent statements are proved in this way. Okay, but this shows that this a priori strand site is actually, I mean, one can work with it. That's the first result. Then another result I want to mention, which is more relevant to the discussion of today, is that the pre-stacks over perf FQ, which I will denote by Bun, which sends S to the groupoid of vector bundles over XSE, and Co flat, which is S perfectoid over FQ to the groupoid of flat Riemann sheaves. Over XSE. These are actually stacks for the V topology. Okay. So yeah, so this is like very specific. one should not expect v-descent results for like vector bundles or coherent shifts or whatever on general adic spaces. This is really something which is specific to the perfect fluid case. On the Fargue content curve is an adic space over E, which is not perfect fluid. But it's not, in some sense, it's not too far from being perfect fluid, because if you extend scalars from E to its completed algebraic closure, then it becomes a perfect fluid space. And so you can prove v-descent results over Pef for vector bundles or such on perfect fluid basis. And then from this, make a little descent argument to conclude that you also have v-descent for such categories on relative Fargue content curves. So the first statement is due to Kedlai-Aliu, and the second one, we prove it by with Johannes Anschütz by actually proving something stronger, that you have v-descent for perfect complexes on relative Fargue content curves. But this is to do this, we use a result of Mann. So the difficult part of the work is really this forthcoming work of Mann. And once you have this descent of perfect complex, really this is what you want for that coherent sheet. Okay. So again, some remarks maybe. So I want to mention another result of Kedlai-Aliu. So a vector bundle P on the relative Fargue content curve, which is fiber-wise on S if E is the vector bundle on the relative Fargue content curve, which is fiber-wise on S, isomorphic to O lambda. So by this I mean that whenever I choose a geometric point of S, I pull back along the. Whenever you choose a geometric point, then you can description of the curve is functorial, so you can just pull back E here, and you require that it's isomorphic to O lambda, so it's semi-stable of square lambda. Is in fact if E is such a vector bundle, then there exists a decover of S such that E becomes really isomorphic to O lambda, not just like pointwise. We use this factor. Maybe another remark is v-descent is useful for like proving various results about vector bundles or flat coherent shifts. For example, something you can, by some by reduction to the case of geometric point. S is a geometric point. An instance of this is the following fact. So you can prove that for any flat coherent sheaf on the relative Fargue content curve, there exists V locally on S an exact sequence of the following form. X SE minus 1 A OXSEN to the power B going to F, where N is in some integer and A and B are also non-negative integers. So you can find such resolutions like globally, but at least after replacing S by a V cover, you can resolve a flat coherent shift by seeing that vector bundles that you understand quite explicitly, which come from like this, from isocrystals.
So, Arthur,
Yes.
I have a small question on the one. It's the first remark. Can one compute H1 in the B topology of GF? H2, I mean the Brauer group, but in the B topology, what is that? Is that 0 or
The Brauer group of what?
of S?
Of S?
Yeah. Because if you say that, yeah.
But so S is any perfect fluid space now of characteristic P.
Yes. It's just suggested by your point one. But don't worry, it's just a question.
I don't quite see the relation between this fact. Here E is not a vector bundle on S, right? It's a vector bundle on XS.
Yes.
Well, how is that related?
Yeah, maybe I should ask the same question not on S but on the X. XS.
On XS. Yeah, I don't know. Maybe.
We're strictly fully disconnected. Shouldn't the Brauer group also be trivial?
Yes, that's what I was. You can maybe reduce to the, in some way, to the claim, for when S is a geometric point. Yeah, so like you can find a V cover by something strictly totally disconnected, so like profinite union of geometric points,
yes.
And then by Fargues that the Brauer group vanishes when S is a geometric point. The Brauer group of the curve, so maybe you can deduce the claim in general.
Sorry, what is written there? V descent is useful for what?
Yes, they claim for proving some results about flat coherent shifts, but as I said, by reducing to the case where you can classify them. Okay. So now I want to say something about, I want to come to Banach-Colmez spaces, so I want to say something about cohomology, vector bundles or flat coherent shift on this curve. Start with a proposition. So again, I fix as a perfect space over a Q. And I also choose flat coherent shift on XS. So notation is, this is the notation I introduced in the theorem. So insist on the fact that this really means a flat coherent shift on XS, not on S itself. Then you can consider the functor which sends T in perfect space over S, so in particular also belongs to this category perfect Q, to the cohomology or analytic topology on the far content curve XTE of the pullback of F to XT. Then this is in fact a V sheet of complexes, which I will denote by like this. Why is this notation? Well, in fact, there is no morphism from XS to S, morphism of Adic spaces, but there is still a morphism from the V site of X for the V site of XS to the V site of S. Also, I did not define what the V site of something which is not perfectoid means, but you could also do it. And then this is really the push forward. You could consider the push forward along this morphism of psi. Claim is that this is just computing by this. You don't need to sheafify. So this is a sheaf, and depending on what the slopes of F look like, you can prove some vanishing results. So first of all, so you always have if I no, okay. So what I want to say is that if all slopes of F, so when I speak about slopes, I mean fiber-wise on S. So whenever I choose a geometric point of S and pull back F to X over this, so far content curve over this geometric point, then I know what vector bundles or flat or coherent shapes look like, and so I can look at the slopes. By convention, the slope could be if you have some torsion, then the slope will be plus infinity. And so if all slopes fiber-wise on S of my flat coherent sheaf F are non-negative, then this actually vanishes unless I is 0. So a flat coherent sheaf with non-negative slopes, for example, a vector bundle with non-negative slopes, has only cohomology in degree 0 on nothing else. And if you instead require that the slopes are strictly negative, pointwise on S, then you only have cohomology in degree 1. I is 1. And so in the first case, so in case 1, I will write C of F for the one which is non-zero, that is just underived push forward. And in case 2, I use the same notation, but note to denote the. Okay, and BC stands for Banach-Colmez, so this is what we call the Banach-Colmez space attached to this flat coherent sheaf. Okay, so the terminology Banach-Colmez space is a bit ambiguous. I mean, there is a well-defined notion originally defined by Colmez after work of Fontaine of what the category of Banach-Colmez spaces is. But since then, the word has been used quite a lot, for example, in the work of Fargues-Scholze in a maybe weaker and more vague sense. And here we do the same. I won't give a proper definition of Banach-Colmez space, but for me, when I say Banach-Colmez space, this is what I mean. So I mean that it means that you have some flat coherent sheaves on the relative far content curve, some hypothesis on the slopes, and you take the cohomology degree 0 or 1. Okay, so it's a V sheaf. So it's a sheaf for the V topology on the category of perfectoid spaces over S. Okay, so this is yes.
So just this V sheaf of complexes is complexes of abstract vector spaces over here or something? Like what is the type of the value of the sheaf on specific perfectoid?
This will be like the half category of sheaves of E vector spaces.
Okay.
On perf S. Yes. over S. These are not all these cohomology shifts are shifts of E vector space. Part content curve leaves over span. So
that does really mean, so E is not really a constant shift, though, right? So E is a continuous function.
Yes, I want to give this example now because it's a bit abstract. So let's look at some examples of vector bundles or flat coherent shifts and see what these associated Banach-Colmez spaces look like.
No, but I mean, even when you're talking about the notion of a sheaf of E modules, like
Yes,
yeah,
I agree.
okay.
Okay, let's look at the simplest possible example. Let's look at the Banach-Colmez space attached to the structure sheaf. So I won't always write a subscript XS. What is this thing? Well, it's actually just given by what Dustin was just speaking about. So-called constant sheaf, but which is not a constant sheaf. So it's an instance of the construction we already saw before. It's just a sheaf which sends S any perfect space over FQ to continuous function on S with value this locally profinite group. And yeah. This is what. So basically, for example, this tells you that if S is a geometric point, what I'm telling you is that the cohomology of the structure sheaf on this absolute far content curve is just E. It's like if the curve is a complete curve over span. Over sections are just elements of the base field. Let me point out that here you see that the relative curve XSE is really not a product S times C. I mean, I would not know what this something would be, but I said several times that you can imagine that this relative far content curve XS is some kind of family of absolute far content curves parameterized by the geometric points of S. But this is some misguided intuition because there is no morphism to S, and here we see that the behavior is really different from what you would expect if you, like, say you have a classical curve, smooth projective curve over a field, and you do a similar thing, then what you should get by this construction is a structure sheaf of S. Something like this. So that's really different, but that's actually a nice feature, as you will see soon. Okay, other examples. Well, again, it's positive slope case, so only degree 0 cohomology. Then, well, using what I said at the beginning about Lubin-Tate, so relation with Lubin-Tate groups, one can prove that this is isomorph. It's representable, this one, by a perfect space. So the V site is subcanonical, so any representable is a V sheaf indeed. It's isomorphic to it's represented by a spa of a power series in a perfectoid variable T over FQ. So it's not analytic. This is the kind of examples we saw in the non-perfectoid setting in my second lecture. It's not a perfectoid space, so I'm a bit cheating when I say it's representable, but if you fix S in perfect Q, if you fix a perfectoid place, then this thing, we saw that already. Base change to over spa FQ, base change to S becomes the it is a perfectly open disk over S. No, it's indeed a perfect space.
Something you already told us about this example, right? You said this was the universal cover of the Lubin.
Exactly. That's how we would check this, for example. So the universal, this Lubin-Tate formal group law, it would be isomorphic to represented by formal spectrum of ring of power series in one variable, because we are dealing with one-dimensional formal group laws. When you do this universal cover, it's like extracting piece roots of the coordinate on this group law. So it's replacing this formal disk by a perfectly formal disk, and this is what we see there.
Can I just so these Banach-Colmez spaces, these are these sheaves of E vector spaces.
Okay, let me. Okay, well, two more examples. The BC of something which is not a vector bundle, but skyscraper sheet. If S is an untilt, S sharp, so it's an untilt of S over E. Then I can look at this introduced before, skyscraper sheet supported at this untilt. And well, what you get in this case, well, again, it's just degree 0, the slope is plus infinity. So you just get, well, homology of the skyscraper shift. So you see that this is just represented by affine, adic affine line over S. Again, represented, it's not exactly correct because this is not a perfect space. But it still makes sense to look at the shift defined by any adic space. Well, okay. Maybe I should have given this example. Okay, like this literal. Sorry, I have to make sense of this. I have to add this superscript diamond, and I realize I did not define this yet. So let me do that later. So I will explain what this means. But I mean, you know what this concretely, you know what this shift is, right? If T is a perfect space over S, what is it sent to by this BC space? It is sent to the unique untilt of T over S sharp. Unique because of this tilting equivalence. Say that whenever you fix a perfectly base, here S, you have a correspondence between perfectly spaces over S and perfectly spaces over S sharp. Oh, functions. And a final example is the case. I want to make a given examples where the slope is negative. So BC space of O minus 1. To describe it, one way to do it is to again fix some untilt. Of S over E, giving rise to the scatter divisor on the curve. And then, well, claim that there is a short exact sequence of shifts like this. O minus 1 going to O, going to the skyscraper shift at S sharp. So, like, this is locally defined by one equation corresponding to this non-zero divisor. Psi inside thing inside the width vectors, and some of this map is just multiplication by this local parameter. So you have such a short exact sequence of shifts on the curve, and then you can take the long exact sequence of cohomologies. These two have only cohomology in degree 0, and this one in degree 1. And what you get is that, because we already computed the BC space is attached to these two, you see that the BC of O minus 1 is A1 S sharp diamond. So again, I did not explain what this, just take this as a notation. I wrote the formula for what this shift is, divided by E underline. So this is the BC of O1 as a B shift on perf S. Okay, so it's a slightly strange object. You model out a smooth, nice, smooth rigid space by locally profiling.
Am I remembering correctly or understanding correctly that so you have this other funny example, BC of O1. That is an extension of A1 by E, is that correct?
That's correct, yes.
Yeah, okay.
You also have a short exact sequence O going to O1. Yes.
Okay.
This is actually, as I said, this is used like in the proof of the classification of line bundles. You start with like, yeah, this exact sequence you mentioned is related to the exact sequence coming from the logarithm of this format. Yes, that's one way to see. At least after you take the last section.
And I'm also remembering correctly that a general Banach space is always somehow built from products of copies of A1 and products of copies of E by some sort of extensions and quotients and so on.
If S is a geometric point, that's indeed correct.
Okay.
But yeah, then in general, well, using these resolutions I mentioned, you can always, if you want to prove for some statements, you can always reduce to and then to like line bundles, and then you do some delissage to reduce to the case either of skyscraper shift or the structure shift.
I see. Okay.
In B should that also should also be a diamond there in example B.
That's not necessary because this is a space in characteristic P, and a perfect, well, almost perfect read up to like base change. So then I really just mean the shift represented by this object. Okay, and I just want to again some remark. I just want to point out two facts that I find rather striking. The first one is actually just a combination of two things I already said. So in Bern, say in Bern n, so let me look at the substack where I fix the degree of the vector bundle to be n. Start at price n vector bundle. The substack corresponding to vector bundles on n vector bundles which are fiberwise from S trivial. Whenever I fix a geometric point of S, I pull back my vector bundle on XS to the file content curve for this geometric point. I want my vector bundle to be just the trivial around n vector bundle. Well, by KDLU, we saw that V locally on S, in fact, such a vector bundle has to be trivial. And we also computed global sections of the structure shift. So this is this BC space of O. And we saw that this is identifies with this V shift E underline. So if you put these two facts together, so this substack, I can call it, I don't know, N0. we have an isomorphism in this substack, and the classifying stack of the V-sheaf associated to the locally profinite group GLN of U. Right? Again, this follows from what I said before. Any such will V locally be isomorphic to the trivial bundle, so there is just one point. And we just then need to determine the automorphism group of the trivial bundle. So we need to see what the functor sending S in pair FQ to automorphisms of the trivial bundle of rank N looks like. And the claim is that this is just this underlying GLN because we are basically because of the example A. So it's in fact, it's non-trivial, but it's in fact an open substack in Bun A. So here again, you see that the behavior is very different from what you would expect if you look at the algebraic stack of vector bundles of rank N and some classical smooth projective curve. So very different. Usual case. Projective curve, well, the substack where the vector bundle is trivial, say, would be more something like whatever the base is, and we modeled by GLN, but seen as an algebraic. Right? Because if instead of XS you have something like X times S, where X is a smooth projective curve over field K and S is a scheme over K. If you look at such a functor, this is just sending S spec A, this is just A goes to GLN of A. Okay? So this is what you see in the classical situation.
No, but the analogy, is that the correct analogy? Isn't it a moving curve over S, the analogy?
Yes, and that's why
it's not a moving curve, it's a constant curve.
Yeah, okay. I mean, when I'm referring to the usual situation considered in geometric Langlands, where you have fixed a curve over K, and then you look at the moduli stack you define is the one sending S, the scheme over K to vector bundles over X times S. Yeah, so it's as a geometric object, it's not very interesting. It's just a product, but the stack itself is something that people work with in geometric Langlands. And this is the kind of thing you would see inside this stack. Whereas here we have something very different. We have replaced this algebraic group by just like the sheaf attached to a locally profinite group. And this is great because this means that sheaves, p-adic sheaves on this are not very interesting. Very interesting because this is connected. But here, they would correspond to representations, p-adic representations of this group. And we have a lot of interesting representations, basically the one which are studied in the local Langlands program. So more on this next time, but I wanted to point it out. And for example, a particular case, if n is 1, so then Bun 1 is just like the Picard stack of this curve. And then you can really completely describe the structure. It's really simple. Line bundles are indexed by the degree, so this gives the decomposition into connected components. The thing I explained for the trivial bundle works as well for O of D. And what you see is just union of the specifying stats. GL1 is just. So this is what this stack looks like. Okay, this was fact 1. Second fact is that the functor I had before, which I denoted by R to over star, In fact, you can consider it for like perfect complexes on this relative part content curve, going to derive category of sheaves of underlying E modules on the V side of S. This is fully faithful. But this holds for any S. So in particular, you have the following identification. If you look at outflow over star of the internal home or inside the category of OXS modules between, say, any vector bundle, for example, and the structure sheaf, then this is isomorphic to internal home in the category, in this category of sheaves of E modules between this formal and E and Z. Well, okay. In some sense, you can think to this as, I don't know, third reality on the curve, on the far content curve.
Because P is always on the left-hand side. Why is that third reality?
Why is that third reality? Well, because, I mean, this is telling you that the dual of cohomology is cohomology of the dual. That's what I think to this as third reality. It's like if the dualizing sheaf was just the structure sheaf on this curve. This is not third reality in any literal sense because the curve is not a finite type over E. It does not map to S. So there is nothing like third reality on the curve, but this statement makes sense. It's true, and I don't know. One can think to it as.
There is no E dual nowhere.
Well, there is, right? This is the dual of E. So.
I get it. Thank you very much.
But there is no dualizing sheaf.
This fully faithful statement is just, it never holds in the geometry.
Yeah, exactly.
It's completely ridiculous.
Imagine you take like the structure sheaf and the skyscraper sheaf at the point.
Yeah.
They are not distinguished by this. By doing this.
Well, if G is bigger than 0, they are distinguished. Right?
Okay, yeah, I was thinking to P1.
Yeah, P1, yeah. But even, I mean,
some kind of maybe analog of this is, okay, I think for P1, which again is sometimes a good analog of this curve, there is still a description of, instead of taking cohomology, which is like taking R home from O, things work better for P1 if you.
yeah,
there is, in fact, this functor is not like is not exact, but you go from one structure to the other by some simple operation, which is actually also the same you have to do when you look at identify derived category of sheaves on P1, coherent sheaves with representation of this quiver. But still, yeah, it's I think it's quite surprising. And the way, so it's something I proved with Anschütz. We will need it for the next lecture. This is a statement. And this reduces actually in a funny way, this reduces to a result of Drinf. We bring computed self-extensions of GA, the sheaf, the structure sheaf on the perfect side, perfect algebraic side, you know, of spec FQ. It proves that there are no, if you look at GA as a sheaf of FQ vector spaces, there are no higher extensions of self-extensions of GA on this side, because you take the perfect side. he did in fact much better. He computed all the extensions like without this perfect case assumption, and then the structure is more complicated, and it's related to was told it's related to the computation of THH of FP. So, but when you go to the perfect side, so you invert Frobenius somehow, then nothing remains in positive degrees. And as Dustin pointed out before, like some statements about BC spaces, you can reduce to the case of to these cases A and C, with some daily size. Understanding, proving such a statement in the end is reduced to computing some extensions on the V side between this kind of objects. To work, but ultimately you can reduce to bring statement.
I want to point out that this is exactly Serre duality, because this a solid cotangent complex of the far content curve over E is trivial. It's 0.
Yeah, I was hoping there is something like this. Okay.
Yeah. So the top exterior power is
0. You mean the trivial?
yes. I mean 0. And so the top exterior power is the trivial sheet.
Yes.
Oh, okay.
So in practice,
Into the identities 1, yes. Anyway.
in practice, in many situations, I noticed that you can, if you have some statements in classical geometric Langlands which involve dualizing shift, you replace it here by the structure shift and it works.
Yeah, but this gives a reason why.
But that's
Exactly
exactly
the top
the
exterior
reason.
power of the cotangent.
Okay, good to know.
Did you say this in solid?
Yeah.
Great. So, okay, let me just finish by a brief discussion of diamonds. So this BC spaces, so this cohomology groups of vector bundles or flat coherent shapes on the curve. So we saw they are defined as V shapes, but in fact they have more structure. And this is there are some kind of geometric objects, and they are like diamonds in the sense of Scholze. So the definition is of a diamond is as follows. So again, you fix perfectly space over Q, and then diamond over S. We also just take S to be FQ itself, then it's not a perfect fluid space. This is a V sheet. Let's say Y on the category of perfect fluid spaces over S. That can be written as the quotient of a certain perfect fluid space. Maybe I couldn't see. By some equivalence relation. So Z here is required to be a perfect fluid space over S. And R is like X times X. Equivalence relation. Represented also by a perfect fluid space. And such that it's a pro-étal equivalence relation, so such that the projection map are pro-étal. So I did not define what pro-étal properly means, and I don't want to do that, but it's just inverse system of étal morphisms. So this is an analog in this setting of algebraic spaces in algebraic geometry. Except that, well, usually one requires Z to be a scheme. Here one requires Z to be a perfect fluid space. And usually one works with the étal topology. And here one instead works with the pro-étal topology.
Now this is a V sheaf of sets.
No, this is V sheaf of sets.
of sets.
Yes. Okay, so this is a general abstract definition. One can prove many basic statements about such objects. Since I don't have so much time left, so let me just again give examples. So first of all, well, tautologicalism, any perfect Lie space C over S defines the diamond over S simply by taking Z H of Z, the sheaf represented by Z. This was
So and the X is Z, right?
the X, sorry?
This equivalence relation, this is the Z person. Yeah.
Ah, thank you. Other example is we saw that any topological space gives rise to a V sheaf. Not all of them give rise to diamonds, but any if T is a compact Hausdorff space, then the sheaf associated to T underline is a diamond on curve S for any. S imperfect Q, and it's even represented by, it's even a perfect Lie space. It's profile. This is how we actually prove the diamond. So first we check that if T is profinite, so it's by definition the inverse limit of finite sets. Okay, finite sets would be represented by finitely many copies of the base perfect Lie space S, and the inverse limits of perfect Lie spaces are still perfect Lie spaces. So in the profinite case, you get this representability statement. And then there is a nice trick that I think also you know, because you learn condensed mathematics, that you take T with a discrete topology mapping to T continuously, and you look at the Stone-Church compactification of this discrete space. This will be a profinite topological space mapping subjectively onto T. And in particular, this will give you the desired cover of T underlined by something, the sheaf attached to profinite set, which is perfect. So that's the basic idea of the argument. Very abstract. Okay. So I started 10 minutes late. So take a bit more time. I'm just write what I said, tricks, consider the Stone-Church of T with a discrete. Okay, more interesting maybe, it is more relevant to p-adic geometry class of examples, is that there is a natural functor from analytic Lie spaces over ZP towards diamonds. And this functor is denoted x goes to x diamond. This is the notation I already used in the example before. how does that work? Well, whenever you have such an analytical space X, alpha in line was a nice example. You can consider the functor which sends S, perfectoid space over a Q, to the set of equivalence classes of Anschütz S sharp of S leading over X. So if X is perfectoid, again, if X is a perfectoid space, but no any characteristic, so possibly over a character, not necessarily characteristic P, X is actually X diamond, sorry, is the same as the sheaf represented by X tilt. This is because of the tilting equivalence. Again, giving yourself a perfectoid space, sorry, yeah, a perfectoid space over X is the same as giving yourself a perfectoid space over X and tilt, over X tilt. And this is why in the perfectoid case, you are just somehow moving to characteristic.
We could call it tilt in general, couldn't we?
Yes, we could. That's right. That's some extension of the tilting functor to all analytical space. Yes.
So related question. So am I right that this is actually a composition of two functors, like one for sheaves over perfectoid spaces over CP, and another which is some push or pullback of some morphism of type?
Maybe. Can you be?
So like if I just replace S sharp by, just test X against like perfectoid spaces and characteristic 0, and then we have like a tilting functor, and I compose them one day at a time.
Yeah, right.
Okay.
I did not get it. But,
Yeah, you look at all perfectoids mapping to your guy and you tilt those. And then you take the Coleman over there, it can be presented in this form.
Yeah, as a remark here, what happens if you take this relative Fargues content curve when you tilt it, take the associated diamond, then it's in fact it really becomes some kind of product. So it's a product of the diamond attached to spar E with the diamond of S, which S being perfectly in characteristic is just be S itself, over spar Q, over the final object purpose of B sheaves on perfect Q, and you still need to multiply Frobenius. So in the world of adic spaces, there is no, except in characteristic P, we saw that like the Fargues content curve was defined like by modeling out Y by Frobenius, and Y was literally a product. And I said this is not true in mixed characteristic, but this is somehow restored symmetry, somehow restored in this world of diamonds where this the associated diamond really becomes a product. And this follows from this identification follows from the discussion I had last time about the relation between the Fargues content curve and T.
Did you say that this function is fully frequent?
I guess it's not, but it is if you remember the morphism to spar QP. Yeah. But it's not fully phased. Like all antiques get mapped to the same space, which is a common. Okay, so I just finished with the proposition on the remark. So if S is in perfect Q, on F is a flat coherent sheaf, and I will assume that we let me move fully about the associated BC space. Let me assume that it has either everywhere non-negative slopes or everywhere negative slopes, always S, then C of F is a diamond. So in point 3, I forgot to say something that how do you prove such a statement? Well, it's a bit tricky in general, but in the smooth case, when you start with something which is smooth over a non-Archimedean field, say, locally you are just étal over the torus. And for the torus, you have a nice perfect. Let's just, if you just look at the case of the torus, for example, like this, and let's assume that the base, I have some non-Archimedean base field, which is algebraically closed, and you have something like this, so rigid analytic torus, saying that the associated object is a diamond in this sense is basically saying that what you want to do is to be able to find a perfectoid space mapping to this, and such that the surjectively onto it, and so that the associated equivalence relation is has this property of being pro-étal. But what you can do is extracting these roots of the coordinate. And this defines a pro-étal Galois cover with Galois with ZP. And so it's this sense, what you have here, this smooth adic space, is the quotient of this perfectoid space by ZP, which is profound. So that's basic idea that you have to improve enough to make it work in general. Okay, and that's one final remark is that if you look now, let me recall that from last time, that 1p is the moduli of effective relative Cartier divisors in 1 on the curve. Namely, the functor sending perfectoid space S to the degree 1 Cartier divisors on the curve. We saw that this is the same as the functor sending S all until S sharp of S over. And this was this correspondence between degree 1 Cartier divisors on the curve and until. So what does that tell me? That tells me that this degree 1 of E is isomorphic to the diamond of E. Right? Because by definition, the diamond of E is exactly this function. And okay. Here I have you have to model by Frobenius action. So here as well you have to model by Frobenius. And so in the first lecture, I explained that you can prove a ramified global class field theory as the Lin did using the Abel-Jacobi morphism. Here you can try to also consider the Abel-Jacobi morphism in degree 1, say. And maybe I will do it after base change to FQ bar instead of working on category of perfectoid spaces over FQ. Let me do it over FQ bar. What does it look like? Well, so it has to go from degree 1 Cartier divisors to equal base change to FQ bar. But I already described both sides. Here I just did it. And doing these base changes to FQ bar is in fact just amounts to replacing E by its unramified maximal unramified extension. And what we have here, we saw before what is still over there, the component of degree 1, it's just the classifying stack over FQ bar of this. Great. And so this leads Fargues. Fargues' observation is this description, this funny description, in fact, tells you that also in this setting, and this is maybe the first case where we see the relation between this curve and the local Langlands program. You can reformulate local class field theory as saying that what is a least L-adic sheaf on this? It's essentially a representation of the veil group, right? Because here's the pi1, the Galois group of E breve is the inertia subgroup of the Galois group of E, and you need to add this action of Frobenius. So what local class field theory is about is proving that any least L-adic sheaf on this, in fact, comes via pullback from a sheaf here, the least sheaf here, pullback along this Abel-Jacobi. Because here you see just representations of E cross and E cross. Well, this is what the abelian local class field theory tells you that abelianization of the veil group is exactly E cross. And you can then indeed prove it, reprove it using this geometric technique initiated by the. Okay, sorry. Yeah, that's all for today.
Right, just the existence of this Abel-Jacobi map gives you like the inverse to the arc map somehow, right? Like when you take pi1.
Yes, checking that the reciprocity map you get in this way is the same as the usual arcing map is precisely by relating. Okay, like what is the fiber of this? So here you parameterize line bundle plus non-zero section, right? So the fiber is I should have said this too, is the VC of O1 minus 0. And because of the relation between ubiquitate formal group laws and this line bundle, you can actually prove that what you are doing is the same as ubiquitate arcing.
I see.
So that's how you relate to construction.
I see.
You don't need, of course, you don't need ubiquitate proof of class field theory, but you need the existence of formal group laws.
Yeah.